Hi everyone, my name is Chen Yudao, and today I'm excited to present our group's research on a critical challenge in natural language processing, finding the right balance between high performance and computational efficiency. Specifically, we will be comparing two popular models, BERT and DistilBERT, on the task of news text classification. To give you a roadmap of our presentation, I will guide you through the following sections. First, I will cover the task, dataset, and the background of our research. This is a section I primarily focus on. And next, our group member will let you look at the models, specifically examine the architecture difference between BERT and DistilBERT. Then we will move on to our experimental setup and metrics, and we will present our results and analysis. Finally, we will conclude with the practical implication of our findings. Now, let's dive into the research background. Please take a look at this comparison. This visualizes the core motivation behind our study. In the current NLP landscape, large models like BERT dominate because they have massive parameters. This allows them to capture complex patterns, but it comes at a cost, higher computational cost. So on the other hand, we have small models which have fewer parameters and lower cost. So this will lead us to our core research question. Can we significantly reduce computational cost while maintaining comparable performance? Basically, we want to see if we can get the best of both the world, efficiency and accuracy, using the techniques like knowledge distillation. So, to answer this question, we need to have a robust benchmark. We choose the AG News dataset. This is a standard benchmark for topic classification. The model takes the raw news text as an input, and it must classify the text into one of the four labels: world, sports, business, or science or technologies as the output. So for the pre-processing, we follow standard procedures. We use the word piece tokenizer, applied truncation and padding to ensure a fixed sequence length, and created a script split for training, validation, and testing. This ensures our results are consistent and comparable. Based on the setup I have mentioned before, we established the specific objectives for our project. Our scientific goal is to quantify the trade-off between performance and efficiency. We are not just looking for a winner. We want to measure exactly how much speed we gain versus how much accuracy we might lose. Our secondary goal is to analyze the error characteristics to understand where the smaller model falls short. And our hypothesis is that DistilBERT can reduce training costs significantly while retaining near BERT accuracy, thanks to the power of knowledge distillation. And next, we will move on to the model architecture part.
Let's begin our technical deep dive by examining our baseline model, BERT-based encased. As many of you know, it's built on the transformer encoder architecture, which revolutionized NLP by using a mechanism called self-attention. Unlike previous model that reads text sequentially left to right, the BERT encoder layer allows it to look at the entire sentence at once, capturing complex linguistic pattern and long-range dependencies. For example, understanding how a word at the beginning of the sentence related to one at the every end. Structurally, the base version we use consists of 12 stack transformer encoder layers. Each layer is a level of abstraction, allowing the model to understand deep semantic nuances. However, this power comes at a cost. With approximately 110 million parameters, BERT is computational heavy. It requires significant memory and processing power to run, which brings us the core problem we are trying to solve. How do we keep the understanding but move the weight? This brings us to our solution, DistilBERT. DistilBERT is not just a smaller model, it's a digital version of BERT. The process relies on a technique called knowledge distillation. In the setup, we have a teacher, the original BERT, and a student, which is the DistilBERT. The student doesn't just learn from the raw data, it learns to mimic the teacher's behavior. It tries to replicate the probability distributions or the soft targets that the teachers pro- produces. This allows the student to learn much faster and more efficiency than if was training from scratch. Architecturally, the DistilBERT achieves efficiency by removing the token type, embedding, and the polar. But most importantly, it reduced the number of layers by half. It used only 6 transformer encoder layers instead of 12. The result is streamingly model with approximately 66 million parameters. The goal here is to retain the intelligence of the 12-layer model, but compares it into 6-layer body. Let's compare these two structures side by side to visualize the transformation. As you can see in the diagram, the core transformer architecture remains unchanged. We haven't altered the fundamental way the model processes attention. We have simply reduced the dips. We moved from 12 layers in BERT to 6 layers in DistilBERT. This structural change leads to a massive reduction in parameters, from 110 million down to 66 million. This represents a model size reduction of approximately 40%. Why does this 40% matter? In a real-world production environment, a 40% smaller model means it fits into smaller memory footprints, can be deployed on edge devices like mobile phones, and potentially costs 40% less in storage infrastructure. But the big question remains, does cutting 40% of the brain result in a significant number model? To answer this question, objectively, we designed a rigorous evaluation framework. We, we established our baseline clearly, the 12-layer birds versus the 6-layer distal bird. To ensure a fair comparison, we run all experiments on identical hardware and measures two key metrics. First, efficiency, measured by the training time per fixed number of epochs. This tells us not to just have to fast the models run, but how expensive it is to run. Secondly, the quantitative performance, measured by the classification accuracy on the AG-news datasets. We didn't just look at the final score, we tracked the VC model trend across epochs. We wanted to see if the smaller model learns differently. Does it coverage faster? Does it hit a veil earlier? Let's look at the results. Let's take a look at the experimental log in the slide. In the top table, we have BERT. You can see a clear, steady progression. At epoch 10, it starts at 0.78 accuracy. By epoch 20, it hits 0.8, and it continues to climb to 0.84 by epoch 50. This indicates that the bird has a massive learning capacity. Because it is so deep, it can continue to refine its internal weights and extract more subtle patterns from the data as training continues. It hasn't peaked yet. is still improving. Now, look at the distal-BERT in the bottom table. The behavior is quick difference. In starting strong, hits 0.78 at epoch 10, the same start point as BERT. By epoch 20, it reached 0.83 accuracy, but notice that happens at epoch 50. It stays at 0.82. This tells us the distal BERT structures earlier. It learns the core concept very quickly, like due to the efficiency guidance from the teacher model. But because it lacks the depth of the original BERT, it hits the performance ceiling earlier. It simply doesn't have the extra parameter need to squeeze out that last bit of accuracy improvement. So, what is the final verdict on predictive capability? The original BERT model, with all this computational weight, achieved a peak accuracy of 0.84. The compressive distal BERT model achieved a peak accuracy of 0.82. When there is an absolutely drop of 2%, we must look at the context. The distal BERT retain approximately 97% of burst performance. Think about the trade-off for a moment. We remove 40 of the model's complexity and parameters, yet we only lose 3% of the accuracy. For most practical applications, unless you are in a scenario wherever 0.1% accuracy is mission critical, this trade-off is incredibly favorable. You got a model that is almost as smart, but significantly lighter and easier to handle.
On this slide, I focus on the efficiency and computational cost of BERT and distal BERT. All experiments were conducted under the identical hardware conditions, so the comparison is fair and directly comparable. In terms of training time, distal BERT shows a clear advantage. For 10 epochs, distal BERT completes training in 186 seconds, while BERT requires 386 seconds. When scaling up to 50 epochs, distal BERT takes 965 seconds compared to 1,896 seconds for BERT. Overall, distal BERT trains at roughly twice the speed of BERT. This reduction in training time directly translates into lower computational cost. Faster convergence also allows quicker experimentation and iteration, which is particularly important in practical machine learning workflows. As a result, distal BERT is more suitable for environments with limited computational resources, while still maintaining competitive performance. Well, in the next slide, I discuss the error analysis and limitations of distal BERT. Due to its reduced depth, distal BERT may struggle with tasks that require modeling long-range dependencies or making very subtle semantic distinctions. Importantly, these errors are not primarily caused by insufficient training, but rather by structural limitations of the model itself. As a result, increasing the number of training epochs does not significantly resolve these issues. This observation helps explain why BERT continues to improve with longer training, while distal BERT tends to saturate earlier. In summary, while distal BERT offers strong efficiency benefits, this comes with a trade-off in representational capacity, especially for more complex language understanding tasks. To conclude, BERT and distal BERT are suitable for different application scenarios. BERT is more appropriate when maximum accuracy is critical. Typical use cases include offline analysis, research experiments, and high-precision text understanding tasks, where sufficient computational resources are available and higher training or inference cost is acceptable. On the other hand, distal BERT is better suited for scenarios where efficiency and response speed are prioritized. This includes online services, real-time systems, and large-scale deployment environments. Despite its smaller size, distal BERT achieves near BERT performance while significantly reducing computational costs. Therefore, the trust between BERT and distill BERT should be guided by the specific trade-off between accuracy requirements and results constraints.